Hello friends, how are you? I hope you are happy and doing well. So today I will be uh, I will practice my presentation in front of you. Right? So good afternoon to everyone. Myself Hemant Kumar Naik, and the topic for presentation is subcritical hydrothermal liquefaction of kettle manure to bio-oil. The effect of conversion parameters on bio-oil yield and characterization of bio-oil. So under the supervision of Dr. Sushil Kumar, Department of Chemical Engineering, IIT Roorkee. Uh, yes, sir. So these are the contents of my presentation. So first I will start with introduction. It- Then literature review, research gap, material and method, results and discussions, and conclusion and references. So introduction. So we can see this is cattle manure, right? Cattle manure or cattle dung. So cattle manure, we know, is a fertilizer. In past, you are using as a fertilizer nowadays also, but and also it is a cheap fertilizer. But due to intensification of livestock, more number of livestock practice, it is now considered a waste product, right? So it is now waste product. So it will cause environmental pollution, right? Environmental pollution. So cattle manure has high content of nitrogen, phosphorus, and nitrogen, and potassium, right? So and that's why decomposition of manure releases greenhouse gases, ammonia, and volatile organic compound into the atmosphere, right? So this is a major drawback, and due to this climate change happen, and formation of haze also there, formation of haze. Right? So these are the thing, and for to cope up with we are coming with solution like subcritical hydrothermal liquefaction HTL. We call it HTL is a potential technology for the conversion of kettle manure to bio-oil. So this is the thing. And since bio-oil combustion emissions are biogenic in nature, right? Biogenic in nature, they may contribute less greenhouse gases emission. And so due to this greenhouse gas emissions is less, and then fossil fuels, right? So currently what fuels we are using are more contribute for greenhouse gases emissions. So if you use bio-oil, right, so we get less greenhouse gas emissions. So bio-oil yield of up to 75% of the feedstock volatile content by weight have been reported, right? So we can produce 75% bio-oil yield. This is the advantage. So this picture shows pathway of the reaction. So first we have kettle manure, then we put we if we use solvent, then we can use solvent also. And so but in case of hydrothermal liquefaction, we only provide the water as a solvent, and then the slurry will be made, and that slurry will go to reactor. Right, some reaction after the reaction temperature and pressure, we can left over with aqueous product, right, solid liquid mixture, and then we have to separate. So first we pass to filter, and also the solid particle left that we call cake, you have to dry, then we can have residues as a biochar, and whatever left is we have to break to remove solvent, so that we can get bio-oil. So this way, uh, research pathway will be there. So now finish. So this is the typical hydrothermal liquefaction process. So in this why means this convert cow dung into biooil using water as a liquefaction medium at moderate temperature and moderate pressure, right? So biomass, we have biomass like cow dung is a biomass, right? So water we use solvent, and after that we set some pressure and temperature, right? So depolymerization of the biomass feed will take place inside the reactor, and then after that we get bioil, biochar, and gas. Right. So this is the hydrothermal liquefaction typical process. So these are some literature use come in the introduction section. So like dry sample will be the fine wood, right? Cargozo et al. 2005. Temperature is around 280 mega, means pressure mean megapascal, ambient nitrogen. Residence time minute 15 minutes. So bioavailability is getting 23.8 to 33.7%. Right? And the corn store Demirabus 1991. Temperature 285. There is ambient condition and air pressure. So residence time was 75 minutes. They are getting 49.2% bioavailability. So it is similar. This type of means different pineapple stumps, poplar chips, sawdust. It's around 55-53% bioavailability. And in case of weight, like swine menu, right? Swine menu, EATL 2,275 to 350. This is the temperature range. And process gas was CO, right? For carbon monoxide, 0.34 to 2.76. And the residence time was 5 to 180 minutes. So they are getting 76.3% bioavailability in volatile content, because in case of weight sample, we have to know volatile content, and based on volatile content, we can calculate yield. Right? So and LG for LG 33%. Domestic garbage, right? Domestic garbage is around 27.6 means volatile content. And sewage waste, right? Sewage waste is around 25.3 to 51.8% volatile content bioavailability. And so now literature review. What I have done literature review. We first in at 2010 biomass symbol is kettle menu, right? So reactor is stainless steel reactor or reactor. Right? Temperature parameters where temperature is around 250 to 360 degrees Celsius, pressure 100 psi, manure water ratio 0.25 to 2, solvent is water. Right? So key findings were maximum bioavailability of 48.78% at 310 degrees Celsius. High reading value of bioavailability is 35.53 megajoule. Major non-polar component were toluene, ethyl benzene, and the xylene. So these are the things. And the Feng et al. 2021 is kettle manure, and in the 500 ml reactor, temperature there is 180 to 300 degrees Celsius. Solid liquid ratio is up to 50%. Solvent there is ethanol. In this case, they are getting higher reaction per temperature led to higher yield of the bioil. So higher reaction temperature led to higher yield of bioil. Maximum yield of bioil is 23 gram per kg. 1 kg we are getting 23 gram of bioil. The main component of bioil is ester, hydrocarbons, and phenol. And next is Mar et al. 2014 wood digestion biomass sample. Batch autocave reactor. Temperature is 300 to 250 degrees Celsius. Solvent water, glycol. And there is both solvent. So maximize the bioavailability and minimize the fraction of vacuum residue. So maximize the bioavailability. Right? Water act as catalyst here and accelerate liquefaction reaction. Right? Water is acting as a catalyst here. Formation of vacuum residue is due to incomplete primary depolymerization. So these are things. Lee et al. 2018 is the livestock manure and the reactor is batch reactor model 4593 for instrument company USA. Temperature is around 310 to 340 degrees Celsius. Retention time or residence time is around 30 minutes. Solvent is water. So water findings. Heavy metals in livestock manure have been migrated into the soil residue 70 to 98% after the hydrothermal liquefaction. Contamination level of copper, zinc, and lead in the solid residue after hydrothermal liquefaction were significantly reduced. So lower the environmental risk level of heavy metal in livestock manure. These are the key findings. Next, we will see some more literature review. So you can see. What he at 2021 has used corn cob cattle manure as biomass sample, and the reactor is 100 ml high pressure batch reactor per reactor. Temperature is around 300 to 360 degrees Celsius. Pressure is around 110 to 200 bar. Solvent is water. The findings for optimal temperature for producing bio-oil at 300 degrees Celsius. Deoxygenation and deamination were the major reaction in hydrothermal liquefaction. Bio-oil from cattle manure and corn cob were both composed of phenol and ketone. Phenol and ketone. So then next is Continental 2020 animal waste slur. Biomass source and reactor stainless steel micro batch reactor 10 centimeter cube volume. Temperature is around 350 to 400 degrees Celsius. Pressure is 1.5 to 2 megapascal. At least use K2CO3. Solvent is water. Okay, so they are getting yield of energy density the biofluid ranging from about 35% for manure, 45% for sewage sludge, 50% for fish sludge. Supercritical condition 400 degrees Celsius result in lower bioavailability as compared to subcritical conditions 350 degrees Celsius. However, for swine and cow manure, higher temperature produce biofluid with the better quality in terms of lower oxygen content. So in the supercritical condition, supercritical condition for swine and cow manure, so higher temperature produces biofluid with the better quality. High temperature produces biofluid with a better quality. Right? So quality, if you want to produce quality of bio-oil, then you can value for supercritical condition. And Thigala and Medgate 2012, Thigala and Medgate 2012, dairy waste, a bench top 300 ml stainless steel reaction pressure vessel, autoclave. Right? Temperature is 250 to 350 degrees, pressure 5.1 to 25.5 megapascal. Catalyst they use sodium carbonate. And so converting raw dairy manure into bio-oil. Its energy conversion efficiency is as high as 67.8%. Lower the CO2 in the dischargeable waste and average by 62%. Production of liquid and production from the and these are the literature used, and after that come to after doing literature reviews, some research gave were obtained. So upgrading processes of hydrothermal liquefaction bio-oil to alkane hydrocarbon. We have to upgrade the bio-oil. So and the inhibition of side reactions of bio-oil to gas, char, tar. So you have to inhibit side reactions. So right, so that we can produce a higher bio-oil rather than gas, char. Which bio-oil, some bio-oil will convert gas tar. So you have to inhibit those side reactions, right? Inhibit those side reactions. A blank catalyst and are removing of breaking the vacuum residue prior to the blank catalyst. Some catalyst means we are taking the vacuum residues prior to recycling. Resulting and denitrogenation is needed for utilization of biofluid as a fuel. Right? Denitrogenation so we can do better understanding of hydrothermal liquefaction and on development of continuous flow system. Right, continuous flow system with energy recovery in the feature. A limited number of studies found on hydrothermal liquefaction of cow dung or cattle manure. These are the research lab. And then material and method. Material and method section. So methodology. What methodology used? Supercritical hydrothermal liquefaction of cattle manure was subcritical hydrothermal liquefaction of cattle manure was carried out in a 1.8 liter stainless steel reactor, that is bar reactor. Right. So this, in each test, 500 ml of cattle manure slurry with 0.5 mole of NaOH also has a was placed in the 1.8 liter reactor. The remaining 1.3 liter air space was purged with the process gas. So this is the thing. Pathway of reactions. So what is the pathway of reactions? Right, so with increase in temperature. So biomass. The first hydrolysis will take place. Unit structure, small molecule will be there. Bio-oil formation takes place, and bio-oil decomposition. So that gas and the char and tar will increase in temperature. This is the simplified pathway of subcritical hydrothermal liquefaction of biomass. Right. Purification method. Once the bio-oil is formed, then we have to purify that. So for purification, we are using solvent extraction. Solid residues in the aqueous product were removed by using Wattman number 1 filter. As the Wattman filter paper is there. So first the step. And after the liquid product was extracted by dichloromethane, right? This is a solvent to remove means which is used to remove solvent, means unknown product, right? So with the volume ratio of 1 to 1, right? Means whatever liquid product is there, like 50 ml. So 50 ml dichloromethane will be used with the volume for 1 hour in a separation funnel, right? And the dichloromethane extract was then treated in a rotary evaporator. Then you have to evaporate also, so that the solvent will remove, right? So and remove dichloromethane at 42 degrees Celsius, 42 degrees boiling point. The remaining liquid was considered bio-oil in this, and then we can say the remaining is considered as a bio-oil, right? So this when the bio-oil is calculation, how you can calculate bio-oil? Right? So bio-oil is calculated as weight of bio-oil divided by volatile content into 100. So where WBO is the mass of bio-oil in gram, VC is the volatile content gram of good kettle menu before conversion, right? Before conversion, how much volatile content is there in the sample. So high heating value, then high heating value is calculated by this formula, empirical formula 3.55 C square minus 232 C minus 2230 H plus 51.2 C into H plus 131 20,600. High rating value is the high rating value, and the C and mass percentage of carbon, hydrogen, and nitrogen in the bio-oil. And then results and discussions. So here, first effect of conversion temperature on bio-oil is there. So effect of conversion temperature. And this is the 250 to 360 degrees Celsius temperature is there. Then the y-axis shows bio-oil, lowest percentage of volatile content. So how much volatile content is there? Based on that, how much bio-oil is operating. So here, what they use the different process here, CO, H2, N2, air. So you can see this square black square represent CO, right? So we can, if you use process gas CO at around 310 degrees Celsius, you can get higher bio-oil than any other process gas. And then black circle represent hydrogen, and the upper triangle is represent nitrogen, and the lower triangle is here. So this is the process gas. So you can see at around 310 degrees Celsius, if you use a CO as process gas, then we can get higher bio-oil, right? So this is the information table. The reason is that you have to provide the reason also. Results discussing. So this is the thing. The effect of process gas and the bio-oil. I already explained, but the reason is this figure shows the within the conversion temperature of 290 degrees, 290 to 330, 290 to 330 degrees Celsius, hydrothermal liquefaction with the CO and H2 as a process gas. CO and H2 as a process gas produce higher bio-oil than nitrogen inert. Nitrogen is inert, so we can get higher yield if you use CO and hydrogen, right? And air. Then nitrogen and air. Was process gas in terms of bio-oil. So the maximum bio-oil yield were 48.78% and 44.728% and 38.498% and 27.978% at 300 degree, 310 degrees Celsius, where CO, H2, N2, and air were used as a process gas respectively. So you can see 48.7 76 weight% bi-oil yield for CO process gas. Right? So the effect of CO on bi-oil is is a drop synthesis. So why we are getting high bi-oil in case of CO? So this is the reason. Right? If we have Fischer drop synthesis, if we use CO, so we have the one H2 molecule and NCO, CO, right? H2, and then this will convert CnH2n plus 2 hydrocarbon into then NH2. And so this is the reason. The reaction will take place if we CO as a process gas. And the next is effect of initial pressure on bio-oil. Right? Initial pressure, important one. So here I have already said different uh, process gas value. So for CO, they are getting higher bio-oil, and for nitrogen they are getting low. Right. So and this is the thing. Bio-oil yield and residual solid. Right. So bio-oil and residual solid. This at white square source, bio-oil yield nitrogen. Yes, and this black square source residual solid yield of nitrogen. And then is triangle bio-oil for CO, and the black triangle, upper triangle, residual solid. So we are seeing yield of bio-oil in the residual solid versus initial pressure of process in PSI. So you can see at zero initial pressure, yield is high. And so for nitrogen gas, yield is high at zero pressure, and for mm, for residual solid, and it's a residual bio-oil yield. Bio-oil yield in case of CO is high, and bio-oil yield in case of nitrogen is is lower than CO. Right? So this is the thing. And the solid, we are getting solid at more solid at higher pressure. So if you want to get higher bio-oil yield, then we have to use less pressure, right? So zero initial pressure, then we are getting bio-oil yield higher. It is recommended if we low process gas pressure, then we can get low bio-oil yield. So these are the effect of initial pressure. The effect of residence time and bio-oil yield. Right? Effect of residence time, how much time the reactants are present in the reactor, right? So bio-oil is important. So why it is shows bio-oil and residual solidity. The direct is residence time in minute. Then 0 to 40 minutes. So here also bio-oil CO process gas is high at 0 minute residence time. And up to 20 minutes it is constant, right? 0 to 20 minutes we are getting same yield, right? Bio-oil yield, and we can have high less residual size in this. And if you provide higher time, then we can get less yield, and residual solid yield high. Residual solid is high in the higher reactor time. So these are the effect of residence time. Right? So now moving forward, and also effect of kettle manure versus water. So how much kettle manure we are using, and how much in how much water. Right? So this is an important parameter. Right? So also, so mass means bio-oil is dark square is black square is bio-oil, and upper black triangle is express side, and the lower black triangle is this product. Right. So if mass ratio of kettle manure to water is less, right, we can have higher bio-oil yield. And as you are increasing kettle manure to water, we are getting less bio-oil yield. And we are getting higher gas product. Right? So if you want to produce more gases, then we have to with higher composition of kettle manure. And And this will reactions. This will be the reactions. And so this is here CHF represent by Y. We have CHXY 1 minus Y H2. And so at higher temperature, water will provide steam and convert CO and hydrogen. So, and CO and then CO and hydrogen will react to CO2 and hydrogen. Right, so here NaOH is also used, right? The effect of NaOH is here there. So NaOH and the CO2 will react with Na2CO3 carbonate and H2O liquid will then form. Overall reaction will be CHXO2 and Y 1 minus H2O, 2 minus Y is hydrogen and Na2CO3. So if you use NaOH, then we are having hydrogen high. So you can get high hydrogen in case of NaOH. So that's hydrogen rich environment. And you have to produce higher hydrogen. This is the benefit. And so that's the and the characterization of bio-oil. Right? So once bio-oil is produced, then it tries also for characterization techniques which are elemental analysis. You can also say that ultimate analysis and proximate analysis and thermochrometric analysis, high rating value, ultraviolet visible analysis, FTIR, Fourier transfer, infrared, GC gas chromatography, GC gas chromatography, mass spectroscopy, same electron microscope, transmission electron microscopy, same thing, and inductive coupled plasma microscopy. So elemental composition of and high rating value of hydrothermal liquid, liquids and bio-oil and other liquid fuels were compared. And so kettle menu where carbon percent, weight percent is around 35.38, and for hydrothermal liquid and bio-oil it is 73.72. Bioethanol is around 52.2. Biodiesel is around 27. Pyrolysis bio-oil is around 4.5. Gasoline is around 85 to 88. So these are similarly hydrogen and C. So heating value, high heating value in case of kettle menu is around 15.16. The bio-oil is obtained in 35.53. Ethanol is 29.84, and biodiesel is around 40.15, and the pyrolysis bio-oil is around 60 to 90 per kg. Gasoline is 46.52. It's in this way. Yeah, done with elemental compositions. And these are typical proximate analysis. S is around 20.6, volatile is around 56.8, so higher volatile is there. C is around 7.8, fixed carbon is 14.9. The cellulosic content is also there in kettle menu. Hemicellulose is around 19.4%, cellulose is around 13.2, lignin is around 10.5, fruit liquid is around 1.1. So these are the cellulosic content of kettle menu. And the GCMS analysis, what they have used, they have done GCMS analysis of diesel, gasoline, and water bio-oil they have produced from hydrothermal of kettle menu. So these are the peaks. So you can see really see not similar. Right? So the what bio-oil is not similar. Some similarity is there for diesel and bio-oil produced from hydrothermal liquefaction. And so this is energy. Some part is similar, but results and after that conclusions. What the conclusions is there? Right. So maximum bio-oil yield of 48.78% was obtained at 310 degrees Celsius with CO as the process gas as atmospheric pressure, and the residence time was 15 minutes. The kettle menu to water mass ratio is around 0.25. These are the inference. It's a higher diesel conversion pressure, longer residence time, and larger mass ratio of kettle menu to water are had negative impact on bio-oil yield because bio-oil was converted to gases and the char are under these conditions. Produce higher char rather than higher rather than bio-oil. So these are the elemental analysis. The higher reading value of bio is 35.53 megajoule per kg on average. So after elemental analysis, we get come up to this. And the ultraviolet visible spectrum showed that bio-oil had conjugate structure. The FTIR analysis indicated that the bio-oil contained functional group of polyalcohol, carboxylic acid, phenol derivative, and alpha beta unsaturated ketones. These are the functional groups present in the bioavailability. Furthermore, GC and GC mesh analysis showed that the bioavailability did not contain C4 to 15 alkane. The bioavailability is what they are producing is now contains C4 to 15 alkane. The major component of gasoline and diesel, which are there in the gasoline diesel. But the major non-polar component were toluene, ethyl, benzene, and So these are present. Ethyl means toluene, ethyl, benzene, and which belong to crude oil, and the aromatic component of gasoline or diesel belong to the crude oil. Crude oil also have this component, that aromatic component gasoline, diesel. So these are the some similarities of oil and diesel. So these are the references which I have used to make this presentation. So those are the, you can see that these are the main paper which I this is the main paper which I have thoroughly read, means I have deeply read and activity. And this is also so you can see this paper is also, so this both paper I have used and also I have read all the papers. After that, thank you guys for being here. I will stop.